The game of cryptography involves two players, Alice and Bob. Alice wants to send a secret message to Bob, but she doesn't want anyone else to read it. To do this, she uses a box called AES to scramble her messages, or what we call encryption. Bob, on the other hand, has the same AES to reverse the process, or what we call decryptions. Unfortunately, Eve also has access to the AES box, and she can read Alice and Bob messages. To prevent Eve, Alice and Bob use a pre-shared secret key to encrypt and decrypt their messages. The AES is designed in such a way that you need to test for the age of the universe to find the right key. This is called symmetric cryptography. It depends on pre-shared one key, or in other words, encryption and decryption use the same key. You may wonder that to exchange our messages, we need to exchange a key first. This looks like the same problem as before. But this is not the case. The main difference is that the key is much smaller than the messages. This is reduce the problem but create a new problem called key exchange problem. To solve this problem, Alice and Bob use a different type of cryptography. In symmetric cryptography, we use the same key to encrypt and decrypt our messages. The new cryptography is a box called RSA, and it is different from AES. The RSA box is designed in a way that it can encrypt using a key and decrypt using a different key. We use a padlock and key analog to explain this. The padlock is called the public key, and we can share it with anyone, while the key is called the private key and we keep it secret. This type of cryptography is called asymmetric cryptography or public key cryptography. Remember, to solve the key exchange problem, we want to send a key from Alice to Bob. We treat this key as a message here. First, Bob generates a public and private key. He sends the public key and the RSA box. Alice uses the RSA and the public key to encrypt the message. She sends the encryption message to Bob. Bob uses his private key to decrypt the message. Now, Bob and Alice can use the key to encrypt and decrypt their messages using AES. But what are these keys in reality? The answer is they are large numbers, more specifically a product of two large prime numbers. And the only thing that prevents Eve from getting the private key is the difficulty of factoring these numbers. But how large are these numbers? The number 2 to the power 256 is described by Grant Sanderson as a stupidly large number.
How big is 2 to the 256? Well, it's 2 to the 32 multiplied by itself 8 times. 2 to the 32 is about 4 billion. Suppose you have a really good computer that runs 4 billion operations per second, and imagine 4 billion of those computers. This is something like 1,000 times the number of computers that Google has. Earth has about 8 billion people, so imagine giving half of every individual on the planet their own personal kilogoogle. Then imagine a galaxy that has 4 billion copies of this Earth. Take 4 billion copies of this galaxy, and we'll call it your gigagalactic supercomputer. Let that run for 4 billion seconds, 126.8 years. Then let it run for 4 billion times that, 37 times the age of the universe. Even still, it falls short of 2 to the 256 operations. You would have to do all of that again 4 billion times.
Is this the number we used in RSA and we want to factor? Actually, not even close. The number we use in RSA is between 2 to the power 2000 and 4000. So the smaller number is 2 to the power 256 times itself 8 times. You may think, with such a large number, our computer will not be able to even store it. This is not the case. 2 to the power 256 has 78 digits. This can be written and stored easily. To store the number 2 to the power 2048, a computer needs only 2048 bits. How much time to take to sum two numbers of this size? To sum this number, a computer needs to add the bits one by one. This will take 2048 operations, which take less than a second. What about the multiplication? To multiply these numbers, a computer needs around 2048 square operations. This will take also less than a second. Now you may think that we can do any operation, even factorization. If you want to count up to 2 to the power 2048, you need to count 2 to the power 2048 times. If you spend 1 microsecond on each number, you will need far more than the age of the universe to count up to 2 to the power 2048. A tool that measures the number of operations needed depend on their size is called complexity. If you have two numbers of size n, if the number of operations needed is about n, 5n, or 100n, we say that the complexity is linear, and we write it as big O(n). This usually takes less than a second to compute. If the number of operations needed is about n squared plus 5n, we say that the complexity is quadratic. This is also take less than a second to compute. If the number of operations needed is about n to the power k for some constant k, we say that the complexity is polynomial. This usually takes from a few seconds to several years to compute. If the number of operations needed is about 2 to the power n, 3 to the power n, or n factorial, we say that the complexity is exponential. This usually takes decades to compute. There are also other complexity like sub-exponential, which is between polynomial and exponential. In this video, we will walk through one of the most fastest algorithms to factor a large number. The obvious way to factor a number is to try to divide it by all the primes until we find the factor. How many operations do we need to do this? A moment of thought will tell us that if n has a small factor, we will find it quickly. So the worst case is when n is the product of two primes near to the square root of n. Even if we know all the primes, which will take more than the factorization itself, we need to try all the primes up to the square root of n. The prime number theorem tells us that the number of prime up to square root of n is n over log n. If n is equal to 2 to the power 2048, this is about 2 to the power 1000 operation, and this is take decades for a computer to do. To avoid the trial division, p and q should be as large as possible, meaning that p and q should be near to the square root of n. A clever way to factor n is due to Fermat. If we write n as a difference of two squares, we can factor n. Note that any odd number can be written as the difference of two squares, as we see here. If p and q are near to the square root of n, this means that this part will be small. Therefore, we try to find it by checking if this part is a perfect square. If it is not, we increase by 1 until we find the perfect square. Let's take an example. If n is equal to this number, then using trial division, we will need to try about 8 million primes before we find the factor. If we use Fermat factorization, we calculate the square root of n. Then we check if the number is a perfect square. If it is not, we increase by 1 and check again. We keep doing this until we find the perfect square. Once we find the perfect square, we can factor n. You may ask, is the square function fast? Yes, the square function is fast and it's quadratic. The worst case for Fermat method is when n has a small prime, exactly the inverse of the trial division. So as we see in this diagram, p and q can't be small and can't be near to the square root of n. We usually take p and q such that they have the same number of bits as root square of n, and their difference also has the same number of bits, something like 2000 and 5000. In this case, trial division and Fermat method are not effective. Let's try the Fermat factorization method on 7185. If we start looking for a perfect square, we will find it after 85 iterations. What if I told you that we can find the perfect square only from the first 5 iterations? If we notice that 86 squared times 89 squares equal 432 squares, but modulo n, using the GCD we can find the factor. But how we get a perfect square from these numbers? Trying all the possibilities will take a lot of time. If we have the factorization of these numbers, we can see that the second and the last number multiply to a square. But hold on a second. To factor a large number, we need to factor a few large numbers? That doesn't make sense. Therefore, we introduce the notion of smooth number. A B-smooth number is a number that has no prime factor larger than b. For example, 7150 has 13 as a large prime factor. So it is 13 smooth, also 15 smooth, but not 10 smooth. Now, checking if a number is B-smooth is fast. For factorization, we need to check all the primes up to the square root of n. But for B-smooth, we need to check all the primes up to b. According to prime number theorem, this is b over log b operation. Therefore, for small b, say 2 to the power 20, a computer can check it in less than a second. Let's see some property of B-smooth number. If we take b equal to 13 and take interval of length 10,000, the first interval has 700 B-smooth number. The second one has 13 smooth number, while the last one has only 1. We can see that the smooth number are less for large numbers. We can increase b to get more smooth number as we see here. Now, let's back to our example. To produce the perfect square, we choose small b, say 3, and check the smoothness of these numbers. If we find a smooth number, we keep it, and it's factorization. Otherwise, we throw it away and move to the next number. Now, let's multiply this equation. Remember, we need the left-hand side to be a perfect square. We can see that this means that the exponent of each prime should be even. A moment of thought will tell us that this is equivalent to the system of equation. We can solve this system of equation using linear algebra and produce the perfect square. A question may arise. Do we have always a solution? To generate a solution, we need the number of columns to be larger than the number of rows. This means that we need the number of smooth number to be larger than the prime less than b. The primes less than b is called the factor base. Let's recall what we did so far. We have a large number n. We want to write it as the difference of two squares. We take a few quadratic equations. The left-hand side are squares, and the right-hand side are not squares. We take a small bound b and check the smoothness of the left side. We keep the smooth numbers and their factorization. We build a system of equation using the exponents and solve it modulo 2. We get a solution and we can use it to produce a perfect square. If we have few relations, checking the smoothness one by one is fast, but not fast enough. We can do better. Instead of checking the smoothness one by one, we can sieve over an interval. The new approach is not exact, but it's much faster. Note that Qx has the following form. This means that Qx is equal to Qx plus p, modulo p, for any prime p. If p divide Q2, then p divide Q2 plus p, and Q2 plus 2p as well, and so on. How this help us? We start with the table. The indices represent x, while the upper cell represents a divisor of Qx. A larger divisor means a higher chance to be smooth. So, we solve the equation Qx equal to 0 modulo 2. If we have a solution, say x equal to 0, then 2 divide Q0. So, we multiply the column by 2. Similarly, 2 divide Q2 and Q4, and so on. So we multiply all even indices by 2. We do the same for 3. If we have x equal to 1 as a solution, we multiply the column by 3, and so on. We keep doing this for all primes up to b, or what we call the factor base. The values that have largest divisor have more chance to be smooth. In this case, Q4 and Q10 have more chance to be smooth than others. You may think that is not accurate. You are right, we don't need to be accurate. we need to find smooth number as quickly as possible. Instead of storing products which take a lot of space, we store the logarithm. Of course, we start by 0 and add log p instead of multiplying by b. How much operation we spend for each? If we have a table of size n, then for p equal to 2, we need to do n over 2 operations. For p equal to 3, we need to do n over 3 operation, and so on. The total number of operation is about n log b. This means, in average, we spend log b for each number. One more thing, we solve the equation qx equal to 0 modulo p for all prime in our factor base. So, does this equation have a solution? If yes, is it unique? If no, what does it mean? Qx is a quadratic, so it is equivalent to find the root square modulo a prime p. This can be done using the Schenck's algorithm and have the following situation. If p equal to 2, then we have one solution. If the legendary symbol is equal to 1, then we have two solutions. If the legendary symbol is equal to -1, then we have no solution. The legendary symbol is a function that tells us if a number is a square modulo p or not, and can be computed effectively. The first two cases, we do the same as before. We multiply the columns by the solutions. The last case means that we don't have a solution. This means that we can remove or skip the p from the factor base, and our factor base will be as follows. There are only one question we did not answer yet. How to choose b? Note that if we choose b too small, say 11 in this case, we have the advantage we don't need many b smooth numbers, only 5 needed. But the chance to find the b smooth will drop, and we may not find any. If we choose b too large, say 70, then we need many b smooth numbers. So we need to balance between these two forces. To solve this problem, we need to find the total number of operations needed and try to minimize it. The total number of operations is: first, to check the smoothness of a number, we need pi of b operation. But we can do better with sieving. We improve this to log b. Next, we need pi of b smooth number, so we multiply by this. Finally, we need to test few numbers before actually finding this b smooth number. The probability is u to the power u, where u is equal to log root square of n over log b, according to a theorem. We want to minimize the total number of operations, so we solve t prime of b equal to 0. This will lead to a solution between these two numbers. Therefore, we take b equal to this, and the total number of operations, or the complexity of our algorithm, is about this number. This is a sub-exponential algorithm that makes it one of the few factoring algorithms that belong to this class. Let's finish with a final example. Let's take n equal to this number. First, we need to calculate b. In this case, b equal to 30. Now, we find the factor base. The primes less than 30. We test the legendary symbol for each prime. If it is equal to 1, we keep it. Otherwise, we remove it from the factor base. Next, we define qx. We fill a table with 0, and we start sieving. We start with the first prime, 2. We solve the equation qx equal to 0 modulo 2. We get one solution, x equal to 1. We add 1 to the odd indices. Next, we solve the equation modulo 3. Now we get two solutions. We add 2 to corresponding indices. We keep doing this for all primes. 5 has 3 and 1 as a solution. 7 has 6 and 4. Next, 11 has 4 and 9. 17 has 13 and 12. 19 has 4 and 15. Finally, 23 has 15 and 14. Now, we keep the numbers that have large value, say 10 or more. We can keep x equal to 4, 13, 15, 37, 46, 48, 53, 60, and 61. These numbers have more chance to be B-smooth, but not for sure. Therefore, we need to check the smoothness of these numbers. If they are B-smooth, we keep them. If they are not, we throw them away and go to the next number. We see that we have 8 smooth numbers. We build our matrix using the exponent of the prime in factorization. One by one, we add the columns to the matrix. We reduce the matrix modulo 2 and solve it. We get this vector as a solution. We go back to our smooth numbers and keep the numbers that have 1 in the corresponding position. We multiply these numbers together, we get the perfect square. We use the GCD to get the factorization equal to 8243. That's it. This method is called the quadratic sieve. This is the fastest method for factoring large numbers between 60 and 110 digits. There are many other methods to factor a large number. Each one has its own advantages and disadvantages. The elliptic curve factorization is faster for a number between 20 to 70 digits. Another method which I find fascinating myself is the polar draw method. This method uses a clever idea to find a factor using the birthday paradox. The best method is the general number field sieve, which is fastest method to factor a number larger than 100 digits. This method works similarly to the quadratic sieve, but use algebraic number field.